day, everyone. Welcome to vectors. We're talking about vectors in calculus right now. And we're not going to do calculus on the vectors yet. We're going to study what vectors are. And just in a plane, so just 2 dimensions right now. What are vectors? How do they relate to the rectangular coordinate system? Well, vectors are basically forces. I have 5 vectors here, W, S, T, V, and U. These are forces that act on something. Notice the longer the vector is, the more force it has. So it's got a direction and it's got a force or a distance. Now, these are not rays. This is not indicating this goes on forever. This is a vector. So the length of W right here is the force on an object. So let's say an object is traveling in this direction, like a boat or something. And let's say U is the current of the river that the boat is traveling on. So if you add these vectors together, you have what we call a resultant vector. And the resultant vector would be this. So the boat is traveling in this direction. The current is pushing it this way. So it means that the boat is actually traveling in this direction. So we would say that this here is W plus U, the resultant vector. And we could do really any kind of operations we want on these vectors. I shouldn't say any kind. We can add them, we can subtract them, and we can multiply them by a scalar. So what I would mean by that is, let's say we do something like this. 2s plus t. So we just take our s, and we want 2 of them, so we're going to double it and add t to it, and now we have a resultant vector, which is the red one. That is 2t plus s. 2s plus t. Okay. And we can also subtract vectors if we wanted to. When we subtract vectors, we just go the opposite direction. So let's say we do, how about we do W minus V. Okay, so we have W. Now V usually goes in this direction, but we're going to flip it. We're going to make it go the other direction. So we are actually going to have this V go this way. And that gives us a resultant vector of this. So it is very easy to manipulate vectors in that way. Adding them together, multiplying by a scalar, subtracting them, those kinds of operations. But what I want you to realize is what a vector is. A vector has direction and distance. You can think of it as slope and distance. You can think of it as slope and magnitude. Another name for distance we use with vectors is magnitude. It sounds more powerful, doesn't it? The magnitude of the vector. What does that mean? How long it is. So W has a bigger magnitude than U because it's a longer line. All right? And you can do the same things on a coordinate grid. So say, for example, let's say we're going to do W plus U. Alright, there's W. We'll start at the origin. U, let's start from the origin. It doesn't even matter necessarily where you put these vectors, because what we're going to do, if we're going to add them together, we've got to go from end point to beginning point. So we got to do it this direction. And then we have a resultant vector. Now I want you to think of it this way. It doesn't matter which vector we put first. For example, if we did the U first, and then from the end of U I put the W vector on it, I will end up in the exact same place. Or close enough, but it really will be the exact same place. Now what I want you to notice is things that we can calculate. We can calculate the magnitude, how long it is. You can kind of see the Pythagorean theorem here, a little distance formula. And we can also calculate the angle that it makes with the x-axis. So we'll be doing some of that. We're going to be converting vectors to rectangular coordinates. We're going to take a rectangular coordinate and make it into a vector. And then we're going to put vectors on each other. We're going to add them, subtract them, multiply them by scalars. So, and you can have as many vectors as you want acting on an object. I could do w plus u, and hey, I'm not done. I want to add t to it. So I'm just going to take that t and throw it on the end. There we go. And now I have a new resultant vector, which is this one. So that's how we're going to deal with vectors. Let's do a few example problems then. Let's show that these two vectors that have these rectangular coordinates would be equivalent. So really, it's just from the point 0,3 to the point 6, negative 2. Is that the same length and direction as 3, 10, 9, 5? Well, what do? You guessed it, easy enough. We just figure out first the magnitude. Now the magnitude we denote with double lines on each side, but it's really just the distance. Good old Pythagorean theorem or distance formula. So what's the distance between 0 and 6? Well, it's 6. And what's the distance between 3 and negative 2? 3 minus negative 2 is 5. This gives us the square root of 36 plus 25, which would be 61. All right. And the direction, which really would just be the slope of u, would equal, what do we got here? 3 minus negative 2 over 0 minus 6. So we get 5 over negative 6. All right, what about the magnitude of v? And you can kind of see what's going on here. The distance between 3 and 9 is 6. The distance between 10 and 5 is 5. There we go. Still the square root of 61. Those are the same. The slope would be 10 minus 5 over 3 minus 9, 5 over negative 6. You have shown because they have the same direction and the same magnitude that they are equivalent vectors. We're going to write the vector in component form. Now for us, component form for a vector is really a bracket like this. It's going to have two numbers, and it's really just like a coordinate point. You might say, what's the difference between a vector notation in component form and a coordinate point? Not much, but it's really like the end point. So if a vector form, that's your end point. Your beginning point, unless specified, is your origin. So vectors will have a magnitude and a direction based from the origin to here. Sometimes vectors are written like this, and we're not going to do it this way. Your book doesn't do it that way. But they use the letters of I and J to represent the vectors in the x direction and the y direction. Now, this is one form we're not going to use. Your book exclusively uses this form, so we're just going to keep it that form for now. All right. So how do we write this in component form that has the initial point of 4 and negative 6 and terminal point of 3 and 6? Now remember, that's going to be a very specific thing. Hey, I said from the origin. Didn't he just say from the origin? Remember, any vector can be written anywhere. So even though this v can be written from the origin that way, if I put the v at another originating point, well, that's my vector. It's the same magnitude, the same direction. It's equivalent. All right. So how do we write the vector that starts at 4, negative 6 and goes to 3, 6? Visually, I think it's pretty easy to see. So if we go to 4, negative 6, 1, 2, 3, 4, negative 6 would be down here. And then 3, 6, 1, 2, 3, 6 up here. If this is our initial point, and this is our ending point, that's our vector. So how do we write that in component form? Well, it's pretty straightforward. what direction is this going? If you think about it, what's the x distance? The x distance is traveling -1, and the y value is traveling +12. So that is our vector form. I'm sorry, our component form of this vector. So if you want to think about it mathematically, is you're thinking about it this way. How do I get from 4 to 3? How do I get from -6 to 6? Right, you just solve it for x. -1, solve that for y, 12. So that's your vector in component form. All right, find the magnitude of the vector. Well, the magnitude is pretty darn easy because that is simply the distance. Well, -10 and 3. Square them just like the distance formula. You have the square root of 109. And that is your magnitude, just like that. All right, vector operations. We talked about vector operations as a geometric exercise. Now what about as an algebraic exercise? Well, pretty straightforward. Our vector u is -7, 12 in component form. So I'm just going to multiply them by 3. So 3u is the vector -21 and 36. Remember, just to iterate, it's not a coordinate point, it's a direction and a distance from wherever I start from. If I happen to start from the origin, it matches up exactly with the point -21, 36. But if I start with another point, it's completely different on a rectangular point system, but as a vector. Remember, distance and direction from a point. All right, u plus 2v. So u is -7 and 12. Let's see, 2v would be 10, 4. And if you add them, you just add their places. -7 plus 10, 12 plus 4. So your component vector for u plus 2v is 316. U minus v. So we're going to start with u again. -7, 12. Now remember, addition is just multiplication. I'm sorry. And remember, subtraction is just the opposite of addition. So I'm going to take v and I'm going to make it negative. Then add them together. So I get -12, 10. So that's some basic operations on vectors. Now how do I find the vector if I'm given an angle? Oh, I'm sorry. How do I find the angle and magnitude of a vector if I'm given its origin and its terminal point? Well, it just happens to be that the initial point is the origin, which is nice, and the end point is 3, 4. And you're going to see very quickly why I chose this problem. 1, 2, 3, 1, 2, 3, 4. So first of all, the magnitude. So if I go to the point 3, 4, remember this is my resultant vector, and I started with the point 3 and 4. Guess what? Pythagorean theorem. So the magnitude of that vector is 5. Remember, magnitude and distance are the same thing. Now, what about the angle that it makes with the x-axis? To figure out the angle now, we use a little trigonometry. Now, we happen to know the magnitude. It's pretty easy to calculate. So we could use sine, cosine, or tangent. But in general, we're going to use the tangent because we don't have to know the magnitude in order to use tangent. Tangent would be opposite over adjacent. So your angle theta is just going to be the inverse tangent of 4/3. Now, be very careful because you're calculators are maybe, most likely maybe, set to degrees. I'm sorry, to radians. Well, they need to be set to degrees. And if you put that in your calculator, the inverse tangent of 4/3 is 53.1 degrees. So make sure you're in degrees for this one. So here's your magnitude. There's the angle. Now, let's do it the opposite. What if we're given an angle and a magnitude? So I know that's a magnitude of 12. I know this angle is 50 degrees. So to find the component vector, I need to know the y value of the vector and the x value of the vector. Well, here's our trig again. How do I find the x value? All right, all I know is my magnitude and I know my angle. I need x. Well, a little trig function there. You got it. The cosine of 50 is going to equal the magnitude of x divided by 12. So, really, what does the magnitude of x equal? 12 cosine of 50. And if you do 12 cosine of 50, you're going to get approximately 7.714, around the 3 decimals. In the same way, your y value, your y component of the vector, is going to be the sine of that angle. Opposite over hypotenuse. So the vector value of y is going to be 12 sine of 50, which would equal 9.193. So just a little recap. If you're looking for the x component, it's going to equal the magnitude times the cosine of the angle. And if you're looking for the y component of your vector, it's going to be the magnitude times the sine of your angle. All right, let's put it all together in one last problem. We have 3 forces. We have magnitude of 75 pounds, which is going to be applied 30 degrees. 100 pounds, be at 45 degrees. And 125 pounds, acting at 120 degrees. So it's going to be a very, very rough sketch, just to get an idea of what we're looking at. Alright, so I'm going to draw these 3. So here is 30 degrees at 75 pounds. Let's just say something like that. Alright, the 100 pounds is going to be longer at 45 degrees, and the 125 pounds is going to be even longer still at 120, so there's 90 and 30 more. So if I put those 3 together, what do you think an approximate answer should be? So let me do this over here maybe, just give ourselves some room. So I'm going to take these angles, or these vectors. We got that one. I got that one. And I got that one. So very, very rough sketch. Our component vector will be here. So I got it in the first quadrant, and it looks like the height is longer than the y value would be bigger than the x value. So just a rough idea. Very rough. However, let's take the roughness out and get right to the problem. So for this first vector, we'll call it vector 1. It's going to equal the magnitude times the cosine of 30. And then the magnitude times the sine of 30. Our second vector, with 100 pounds of force applied at a 45-degree angle, oops, that would be wrong. And our third vector, 125 pounds of force at a 120-degree angle. You can use all your unit circle knowledge and all that fun stuff and try to come up with an answer, but you know what? I just plugged it all in the calculator. The resultant vector, so I'll call it V sub r, the resultant vector, after I added all of these together, I got, let me get to there, I got 73.16. Then when I added all of these components together, I got 216.46. All right, so does that point up there seem like it could be 73.16 and 216.46? Possibly. All that we know is that was a rough guess as to where the answer is, and it seemed to match. So this is your resultant vector. From a resultant vector now, we're going to figure out the direction and the magnitude. So the magnitude would be this distance. That would be what we're looking for. And the direction would be the angle off of the x-axis. So the angle off the x-axis, if you recall, would just be the inverse tangent of this value. And when I put that in the calculator, I get the nice little answer of 71.3 degrees. Well, it seems fair, 71.3 degrees, not bad. Now the magnitude of that resultant vector is the distance. So we're going to do the Pythagorean theorem again. We're just going to do the square root of 73.16 squared plus 216.46 squared. Throw that in the calculator, and we get a nice magnitude of 228.5. So what this is saying is that the result of those three forces gives you 228.5 pounds of pressure applied at a 71.3 degree angle. All right, so there's your little foray into vectors in the plane. I hope you enjoyed it. If not, I don't know what to tell you. We only got a couple more things to go. The next video, we will talk about vectors and use a little calculus on them. So until then, have a wonderful, wonderful day. Bye.